All right, any questions? Test corrections. So you've got the test 1A test corrections. The target is this Wednesday. Test 1B corrections. Let's see, today's the 16th. Why don't we just say November 1st?
I never got my test 1A back.
Do you deserve to get it back?
I hope so.
Remind me at the break and I'll go.
Okay, thank you. And when we're working on test corrections, are we able to go to the tutoring center and talk to them about it?
Yep.
Okay.
The ideal is it's a second chance to learn the material. So that's, and you're trying to, and when you do corrections, you're trying to convince me that you understand how to do the problem.
Right.
So on this test right here that I just handed back, I just posted most of the answers on the supplemental material old tests. So there's a copy of the old test in case you want to print one up to do corrections on a brand spanking new thing. But overall, I was pleased. I will say that one of the thoughts that went through my head is I need to make the next test harder. But then I thought that really is unfair. So I will try not to make it harder just because you did well on this one.
What are we covering today?
There you go, test one.
Oh, thank you. Oh, I got the exact same score.
All right, so we were dealing with types of collisions, perfectly elastic one-dimensional collisions, so let's start there. One-dimensional. And so I have some mass 1 cruising along with some initial velocity V1 initial. I have mass 2 cruise along at some V2 initial. And I'll just say to the right is positive. And then after the collision of M1 final, cruising, I'll have M1 cruising along at V1 final, and mass 2 cruise along at V2 final. They don't have to come towards each other. You can get collisions where their velocities are in the same direction. If one of the velocities is going the other way, then you'll throw a negative in there. But this works for generic. Perfectly elastic collision, what does that mean?
No energy is wasted in like crumple zones of a car or deformation of the objects.
More specifically, on the energy.
No
Oh.
loss as heat, that is. No heat loss.
All energy remains kinetic energy. It doesn't transfer into other forms.
Okay, kinetic energy is conserved. Yeah, all the stuff that you were saying is correct. I was just shooting for something more targeted. And I have a collision here, regardless of the rest of it. If I have a collision, what else is conserved?
Momentum.
All right. So I got two equations. Assume that I know my initial velocities, I know the masses. So my unknowns are the final velocities here. Just for the sake of ease, I'm going to make that capital A, B, C, and D, just so I don't have to keep writing subscripts. So my conservation of momentum, my P initial equals P final. I get M1A plus M2B equals M1C plus M2D. Just mass times velocity. So dramatic pause, are there any questions on this? Like, well, you look like you want to ask a question, so that's fine.
So are like C and D supposed to be after collision
Yes.
velocities? Okay.
Yeah, make that more explicit before.
No, the thing that got me is the C and the D kind of came together to look like parentheses, and I was
Oh.
very confused about the notation.
I see where you're coming from on that one. Yes, that would be confusing. No, it's the final velocities.
Right.
Post collision. All right, other questions? All right, because we have a collision here in a closed system, we have momentum is conserved, and then the fact that it's perfectly elastic, we have kinetic energy conserved, so K initial equals K final. So 1/2 M1 A squared plus 1/2 M2 B squared equals 1/2 M1 C squared plus 1/2 M2 D squared. Hopefully looking less like parentheses. Again, C and D are our unknowns. Now, I'm not gonna take this, solve for D or C, plug in, do the quadratic formula. We could do that, but there is a simpler way of solving this. So, what I'm gonna do is I'm gonna get the M1 terms together and the M2 terms together. So in the first equation, that brings bringing this over here and this over here. So I have M1A minus M1C is equal to M2D minus M2B. It's just the momentum equation where I'm combining the like masses. I'm going to factor out mass 1. A minus C equals M2 D minus D. Questions to hear?
So you're saying the change in velocity of one is equal to the change velocity of the other?
Well, it's offset. If the masses were the same, that would be true,
Right.
but just mass 1 times its change in velocity.
Okay.
Actually, this is the negative change in velocity because A is initial and C is final. So that would be the negative of the change.
So why is it flipped on the other side? Why is it D minus B, but on M1 it's A minus C?
Because the D term is positive here. When we bring this over, that's
Okay.
subtracted. All right, so let's do the same thing for the other equation. Actually, let's simplify it. What can we do to simplify that second equation?
Multiply everything by 2.
Yep, there we go. Now we'll do the same thing. So I got M1 A squared minus, we'll put an extra step. M1 A squared minus M1 C squared equals M2 D squared minus M2 B squared. We're going to factor them. So this is the energy equation. So I have M1 A squared minus C squared is equal to M2 D squared minus B squared. We can factor it one more step. How does A squared minus C squared factor?
A minus C squared. Oh, are you looking for like?
What binomials multiply together to give us a squared minus c squared?
A minus,
Is it, A minus C, A plus C?
That's it. So it's a minus c, a plus c is equal to m2, d minus b, d plus b. We haven't combined the two equations yet. All we've done is just treat each one separately. Now let's combine them. The math people, and I'm assuming they're not lying to us, say that if I divide both sides by the same thing, I'm good to go. That if that's true, then if I divide by the same thing, it's also true. So I'm going to divide the left side by m1 a minus c. And I'm going to divide the right side by something equal to that, m2 d minus b. Because right there, from the momentum equation, they're equal to each other. So what am I left with once I divide those things?
A plus C is equal to D plus B.
I assume you said b.
Yeah.
If I put it in slightly different terms here, I get a minus b. Switching these back over is equal to d minus c. This is the relative speed of approach. Equals the relative speed of recession. So from B's point of view, how fast is A coming towards it? And then after the collision, from A's point of view, how fast is B going, is the second mass going away from it? So that problem that we had last time, what were the numbers? What were the masses?
If this is the set, or that was perfectly inelastic, and one of them we had 3 and 4 kilograms. I don't know if that's the same one.
I don't remember either. What were the velocities?
6 meters per second and 2 meters per second, but these were going towards each other. I guess.
Let me take a quick gander at your notes just to see since you were unsure.
This was perfectly inelastic.
Okay, they stick together there.
I don't have
And
any
then
word.
down here, got 3 and 4. It's looking like I used the same stuff, just perfectly elastic the second time. All right, so my equations to solve here. I got conservation of momentum. So I have 18 minus 8 is equal to 3c plus 4d, where c and d are the final velocities. Pause, because I skipped some steps there. Are any questions about where I got the 18 and the 8 and the negative 8?
no.
All right. The second equation, last time we did this, the second equation we used the conservation of kinetic energy.
Wait, I'm sorry, we're talking about velocity here, so it's meters per second. What units?
Would that be?
Yes.
Well, it's momentum. It's mass times velocity. My mass is 3 kilograms. My velocity is 6 meters per second. So you get 18
Right.
kilogram meters per second. Okay, nothing fancy. Some people prefer Newton seconds. And some people just make up a unit, define it, and then use that. All right, other questions? So the second equation, we're gonna use this right here, whichever form you want. Take that one. So I have A minus B, well, A is 6, that's my A, that's my B. So I have 6 minus negative 2 equals D minus C. So D is equal to 8 plus C. I can plug that into here. So I have 10 is equal to 3C plus 4, 8 plus C. So that's 3C plus 32 plus 4C. And so I get, squeeze it over here. Negative 22 is equal to 7C. So C is equal to 3.1428 negative meters per second. And D, well, I know it's 8 plus C. So 8 plus that, which is 4.857. Let's go, right? All right, questions? Is that what we got the last time? For the perfectly elastic?
Yes.
Okay. Now, when we did this the last time, when we used the quadratic, we had two solutions. Doing it this way, we have one solution. What happened to the other solution?
Isn't the other solution like the initial?
Yes. Where did it go? Why do we not get that one? There was a specific step in our derivation where that solution dropped away. And hence, it's on that board over there.
When we divided the second by the first solution, third
Yeah.
equation.
The non-collision solution, where the initial condition is the final condition, A and C are equal to each other, and so we'd have 0 in the denominator. Math people still have not figured out how to divide by 0. So, dividing both sides by the same thing works as long as it's not 0. And so at this point right here, we eliminated the solution of the non-contact. This technique obviously has the advantage of we're not dealing with quadratic. The math is significantly simpler. It has the disadvantage of the fact that we don't have a built-in check. The other way we get, I know one of the solutions is going to be they don't hit each other. So if I get my initial condition as my answer, as one of my answers, I know I've done something right. This way you don't have it. But the math's simpler. So at some point you're going to make the judgment call about which technique works best for you. And I'm about to show a third technique, which is the one I personally prefer. Questions before we solve this yet again?
be the last time? So this time we're combining conservation of momentum and kinetic energy. What was the last?
The last time, we basically solved for C or D, and then plugged it into this equation here. And
So
we
it's
ended
the
up
same,
with,
except we did substitution instead of division.
right. I think your question was answered, right? Okay. Other questions before we do a third technique, which is conceptually more difficult than these. But I think the math's easier, but that's just personal.
I feel like I'm getting lost in the weeds here, but momentum just confuses me that it's found by just multiplying them together. I'm just so used to foot-pounds and the idea that velocity should be squared. Like if the velocity is increasing, the amount of energy is increasing linearly.
If the velocity is increasing, that means the speed's increasing.
Yeah.
Well, depends on what you mean by velocity increasing, but if you're going faster and faster, your kinetic energy, it's not a linear relationship, it's a quadratic relationship.
Right, yes. But here, wouldn't it be a linear relationship? If it's just mass times velocity is equal to your momentum.
Yeah, that would be a linear relationship. So in essence, from a math point of view, what you're doing is you got a parabola, and then you have a linear relationship, and you're just seeing where the two meet.
Okay.
I guess if you're plotting D versus C or C versus D.
Okay, I understand. I missed. I should have paid attention more to that right there.
All right. Feeling somewhat subtle?